We're moving on to section 3 of chapter 9, and we're going to be dealing with limiting reactants and percent yield within this section. It's going to piggyback off of the stoichiometry. You're going to need that too, so have a periodic table and a calculator handy. Limiting reactants. First off, just a couple of definitions. The limiting reactant is what's used up in a reaction, and it determines how much product you can make. Your excess reactant is going to be added to ensure that all of the other reactant is completely used up, and it's usually cheaper and easier to recycle. So for the limiting reactant, step number 1, you must write a balanced equation. So you got to find out what those coefficients are. Step 2, for each reactant, you will calculate the amount of product formed. Let me just add a little side note into here. You can calculate, doing your stoichiometry for each of your reactants through the mole ratio step. Stop, you'll have answers for 2 reactants, and then assess which is less, and then finish to find out the full answer for your limiting reactant. Just know I will bring that up again once we're working through a problem. Your smaller answer indicates the limiting reactant and the amount of product that you can actually form. So let's move on to a problem dealing with limiting reactants. We have 79.1 grams of zinc reacting with 0.9 liters of 2.5 molar hydrochloric acid. Identify the limiting and excess reactants. And once you find that out, how many liters of hydrogen are formed at STP? So we're going to write down this equation. We're going to balance it, write down all of our given information, what it is we're looking for, and then head on to the steps for limiting reactant. So as a refresher for this reaction is a single replacement reaction. Zinc and hydrogen are going to swap places to create our products. Once you balance the reaction, the coefficients are 1, 2, 1, and 1. I'm going to write down all of the given information. We have 79.1 grams of zinc, and we have 0.9 liters of hydrochloric acid, and the strength of that hydrochloric acid is 2.5 molar. Just like we did in the previous section, we're going to change that capital M to the units it really represents, which are moles per liter for molarity. And the other part of that, it wants to know how many liters of hydrogen at STP can you create. Now, this problem does deal with liters, dealing with molarity and molar volume. So hydrochloric acid being in the liquid phase, that's where our molarity's at. Hydrogen gas at STP, we're going to be dealing with molar volume there. So that 22.4 is going to get used at some point. So we've got to take both reactants and work out their own problems. So let's start with zinc. For zinc, we have 79.1 grams of zinc. We're going to change it all the way to liters of hydrogen. So grams of zinc has to be put in the denominator. And we go from grams to moles. Again, I'm thinking of those boxes from earlier in chapter 9. That's molar mass, dealing with zinc. So I go on my periodic table, find the molar mass of zinc. The grams from the periodic table are 65.39. Cancels. And I'm ready for my next step, which is moles of zinc. That sets up our mole ratio, because that's moles of known, moles of unknown is hydrogen. And we're going to put our coefficients in. The coefficients just happen to be 1 to 1. These cancel. Now this is what I was saying earlier. You could stop after the mole ratio step within each of these reactant swap overs to product and then finish out with the last step. I'm going to go ahead for this case and finish out with the last step anyways. We don't want moles of hydrogen. we want liters of hydrogen. And you can go, if you have grams to moles, once you're at moles, do your mole ratio step. That's this one right here. And then we can go to molar volume, which was liters per mole for molar volume. Still dealing with hydrogen. So that 22.4 has to go with liters. It's 22.4 liters per 1 mole of the gas. When you calculate that out, again, multiply everything on top, divide by all the numbers on bottom, you get 27.1 liters of hydrogen gas. So if all of the zinc reacts, you could produce in this reaction 27 liters of hydrogen gas. Now I'm going to take my other reactant, which is the HCl. Again, we're going to start with the liters portion of it since there's two numbers given. We've got 0.90 liters of HCl. And those units need to change. We can go from liters to moles of HCl. And as I look back up at my given information, there's the liters and the moles. I'm going to put in my 2.5, which was given, over 1. I have officially used both of the numbers that were given up at the top. And liters cancels. I've got moles of HCl. Moles of HCl has to go on bottom. That's moles of our known. The unknown is still hydrogen gas. And this is where we add our coefficients. So the coefficients are 1 and 2. Those units cancel. So moles of hydrogen gas, we've got one more step we've got to get in. So again, you could have stopped. I'm just going to make it right here. You could have stopped there, gotten your answers, and then proceeded on with this last step because the last step is going to be identical for each one. But again, I'll leave that up to you. Just as long as you show all the necessary work, we are good to go. So moles of H2 down here, and we can go from moles to liters since now we're dealing with the molar volume of a gas, and that's where that 22.4 comes back into play, and that last step, again, is identical for each one of these. Multiply all your numbers on top, divide by what's on bottom, you get 25 liters of hydrogen gas. So as I look at these two, the number that I have the least amount of, 25 liters of hydrogen, makes HCl my limiting reactant. So HCl is my limiting reactant, zinc is my excess reactant, and the product that would actually form is going to be 25 liters of hydrogen. So if we were to look at a picture of this, you could see putting the zinc down inside the hydrochloric acid. Some of the zinc is still going to be left over as zinc that does not fully react with the hydrochloric acid based on the concentration of acid and the amount that is being used. Okay. Again, a lot of math work. Make sure you show all of it. Next up, we're going to look at percent yield. Percent yield is a type of efficiency. It's the actual yield divided by the theoretical yield. So your actual yield is what you would measure inside of a lab. The theoretical yield is what you calculate on paper. The actual yield, though, is going to be less. Maybe I should write that down for you. The actual yield will be less since you're going to be dealing with impurities caused by or some byproducts that might be involved in side reactions. Also, too, probably a little bit of human error in there. So when we talk about percent yield, we are looking at even almost like a percent error type calculation. So let's get to a problem dealing with percent yield. So potassium carbonate and hydrochloric acid give you potassium chloride, water, and carbon dioxide gas. The problem says you have 45.8 grams of potassium carbonate reacting with excess hydrochloric acid. So we don't have to do limiting reactant since it's already in excess. You have 46.3 grams of potassium chloride that is formed. I want you to calculate the theoretical and percent yields of KCl. This will be the only problem we do like this within the podcast. Just know when I give you a worksheet, some other problems to do, we could easily be moving backwards, maybe percent yields given, and you've got to work backwards to actual or theoretical yield. So watch how the information is given so that you can decipher it properly. It's really nice of them to go ahead and give us a balanced equation. I'm going to add the coefficients back into here. 1, 2, 2, 1, 1. The information from the problem, it says we have 45.8 grams of potassium carbonate given, excess HCl, and it wants to know how many grams of KCl can be formed, but we've got to find that because of the theoretical and percent yield. So the actual yield says 46.3 grams of KCl are formed, but theoretically calculated on paper, we've got to go and do the calculated yield too. That's why the question mark is also underneath KCl. Once we find the calculated yield, then we can do percent yield. So starting off with this right here, our given information, we've got to start with the potassium carbonate. We're assuming again all the reactant is going to be used up. So looking for our theoretical yield here. So theoretical yield is what we're calculating. 45.8 grams of potassium carbonate. We don't want grams of potassium carbonate in our answer, so we're going to put it down here to get rid of it. But we can go from grams to moles of potassium carbonate. Just erasing a stray mark. That is molar mass, so go to your periodic table. From the periodic table, I know based on 1 mole of potassium carbonate, the mass of the two potassiums, the carbon, the 3 oxygens is going to be 138.21 grams. 138.21 grams, and you can show that off to the side on your paper. Make sure you know how to calculate it. These units cancel. We're left with moles of potassium carbonate, which is not what we want. But that is moles of known. So we have to go to moles of unknown. Our unknown is KCl. This is where we do our mole ratio step and use our coefficients. KCl's coefficient is 2. Potassium carbonate is 1. Those units cancel. That stops at moles of KCl, but we have to get to grams of KCl. So when I continue to go, moles of KCl here, I can go from moles to grams. That's molar mass again, just this time it's reversed. So go find the mass of KCl. That's 1 potassium and 1 chlorine atom. When you add up those masses from the periodic table, you should get 74.55 grams. Multiply all the numbers on top of the line, divide by the numbers on the bottom of the line, and you will get 49.4 grams of KCl. Please make sure you double check your math that you can calculate that. So theoretically, calculated on paper, our theoretical yield, if everything went perfect, is 49.4 grams of KCl based on how much potassium carbonate we started with. So that is the theoretical yield. Notice it is more than the actual, which it has to be because our percentage we can't have over 100%. Now we go and we look up percent yield. That was actual over theoretical times 100. Actual was 46.3 grams. Theoretical, 49.4 grams times 100. And that percentage is 93.7%. 93.7%. Again, please get used to theoretical, actual. I know some of these problems can be confusing that we're going to get to, so make sure you have it straight in your head. Show all of this work in your notes and in your homework.